back. Hopefully everyone is having a good start to your week and all of that. Today we've got a few announcements first, and then we're going to start lecturing on chapter 4. Towards the end of class, I'm going to set aside a little bit of time to go over material very quickly, kind of highlight the things I think are important for the exam. So class ends at 5 after. So let's say if I get to 11:45 and I haven't stopped, shout at me to stop. That'll give us 20 minutes. I think that should be enough time to go through the things for the exam. So everyone is aware the exam is Thursday in class, so prepare accordingly. That exam is going to cover chapters 3 in its entirety, and then most of chapter 2, so from the experiments on in chapter 2. So that's the parts of the atom, the property of those parts, finding out how many you've got of each, and then the placing of electrons and so forth as we go through it. And we'll talk some about those types of things later on. And then chapter 3 is the periodic table. So all the different parts of the periodic table and so on. That. And I think we finished chapter 3 last time, right? And then I held off on chapter 4. So that is that. The format is going to be exactly the same as the last exam, multiple choice fill-ins. Probably about the same number of questions roughly, more or less. I haven't finished writing it yet, so kind of hard for me to say, but I'm aiming for basically the same thing. Tables that you're going to get. You're going to get a periodic table, as always. You're also going to get an electronegativity table. We talked about electronegativity a little bit at the end of chapter 3. I'm not sure what you would use that for, but it's there in case you need it or want it. And then also you're going to get the Aufbau principle, the little zigzaggy chart showing the filling order for the quantum notation. So those 3. I think that's everything I said I'd give you, but if there's anything else, just let me know and I'll remember it. But I think that's everything. So those will be at the end of your exam as usual. Questions about that at all? No? Okay. Everyone doing okay? Everyone awake? It's rough on a Tuesday? Okay. 10 o'clock. I guess in 2 weeks we have fall break. So that's something
How
to look
long is
forward
that?
to.
Is it just that Wednesday, Thursday?
I think it's
It's that Monday and Tuesday.
Monday, Tuesday.
Monday, Tuesday.
Monday, Tuesday. The reason why they do that as 2 days is because it pairs up with Thanksgiving. So at Thanksgiving, you get Wednesday, Thursday, Friday off, so you get a whole week off during the semester.
Nice.
So Monday, Tuesday, and then later on is Wednesday, Thursday. So like lab classes that meet once a week or something, you don't have out of sequence for the different days and so forth. So yeah, we got that to look forward to. That would be nice. About the time that is due, actually the day after we get back, I have to have my grades in, but that's the midterm point for the semester. And with the midterms, I'm going to calculate midterm scores for everyone and turn them into wherever I turn them in. I think it's my NKU. So you guys can see those. Now, if you missed an exam, there's a couple people that missed an exam, that's still going to count as a 0 because I don't have the final to substitute in for that. So if you're in that boat, don't panic when you see it. Right? A huge chunk of scores there. The other thing about panicking when you see your midterm, if it's not as high as you want it to be, don't panic. Because in terms of the number of points for this course, we've actually covered a very small amount of the total number of points. The midterm is going to include the second exam. But after the midterm, we still have the third exam, the fourth exam. We have the final. We have the topic paper due. You can improve upon all of your homeworks. We have a couple more clippings due as well. So all of those points add up to much more than we've had up to this point in the semester. So even if your score is not as good as you want, then you can still bring it up without a problem. A lot of people panic. I had people after the first exam saying, I didn't do as well as I wanted. I failed it, am I gonna pass your course? Well, absolutely you could. I mean, 200 points out of 1,500 or something like that is not that big of a deal in the grand scheme of things. Now that being said, you don't wanna continue on that path if you're in there. So you need to evaluate things and how you're studying and so forth. It can be done. When I was in undergrad, my first semester I was taking 4 classes and I got 4 failure notices at midterm. But I changed things around and I actually didn't get kicked out. You can imagine me still being here. Yeah.
Did you say sometimes after a test there may be the possibility of like another puzzle or something?
Yeah, so we'll have an extra credit after each of the exams. They'll be roughly the same percentage. It won't be another periodic table, it'll be something else. But every time we'll do something for a little bit of extra credit there. The way the course is set up, the exams are not the end-all be-all of your score. I mean, they're a large amount of it, obviously, because they're exams and so forth, but technically, you can have a failure average for the exams and still get a C in the course because of all the other points and so forth. But I'd rather have everyone get a B on all the exams and then an A in the course. But, you know, that's how it is. I don't like when I went to undergrad, almost all of my courses were 3 exams and that was your score for the course. Failed one of the 3 exams and the best you could do was a C for the course. So, yeah, I don't like that philosophy, so I don't do that at all. That's not my intention. So, midterms will be calculated. Also, midterms for that, I'm going to count homeworks 1 through 3 as the ones that are due in terms of calculating the midterm scores. So, if you haven't done homeworks 1 through 3, then that will bring down your score a little bit. You can still do them and everything before the final grade, but just so you're aware of that. Yeah, and then quizzes, if you missed one, it'll hurt you a little bit at this point, but it won't in the end because I dropped one out, and then we'll calculate in the final grade. Okay, so that's the midterm. I don't know, you guys got any questions about that? No? I don't know if they still mail them home. I guess I assume they probably do, but I don't.
No, what?
A little piece of paper saying you're failing. Yeah, they used to. I don't know if they still do with the new system or not. So I always used to tell the students to get home and get the mail before the parents if they cared about that. But that may not be.
They post it online as well too, right?
Yeah, they post them online for you. So that's why I turn them in. It's through my NKU. So I don't know how they alert you. But there you go. And then finally, extra credit. Remember we have the extra credit for exam 1, the crossword puzzle. It's not due, I don't think, until like a week from the exam, I said. So at any point you can hand it in. If you've got it done, just drop it off and so forth, and I'll get it up on the blackboard for you. And then we'll have another extra credit after the next exam. So that's my list of announcements. They all make sense? Everyone good with all that? Okay. Anything else bothering you at this point? So what we're going to do then is we're going to get started on chapter 4. And in chapter 4, what we're actually looking at is chemical bonding. So up until this point, we started out first with what is science and what is chemistry. And then right away we started talking about atoms as a fundamental particle. So we've spent the last couple chapters talking about atoms, looking at what makes up atoms and why we put them on the periodic table the way that we do, and different trends of the periodic table. So electronegativity being the highest, the top and right of the periodic table, metals being to the left of the periodic table and so forth. But it's all been about atoms up to this point. Now in chapter 4, we are going to switch from talking about individual atoms to combining atoms together to form chemical reactions. So a chemical bond occurs when two or more atoms interact together and form a bond. We're only going to be talking about two atoms. So two-atom chemical bonding as we go through the course. And this is really the basis of chemical reactions. So we've got iron plus oxygen. It goes to iron and oxygen chemically bound together. This is an atom of iron, an atom of oxygen, and they combine together to form a compound. And this is the gist of what chemical bonding is. So two atoms interacting together and bonding together. So bonding, you can think of it in the most basic terms of sticking together. There's a couple different ways to stick together, and we'll talk about that through the chapter, but that's the gist of what we're talking about. Now, to understand chemical bonding, we really have to understand valence electrons. We've talked about these time and time again, and it wasn't by accident. Valence electrons control chemical bonding. So you don't have to understand really much else about atoms except for their valence electrons. And that's really the key part to understanding why things behave the way they do. Sodium on the periodic table, number 11, has one valence electron. Lithium has one valence electron. Potassium has one valence electron. They all undergo the same type of reactions because that one valence electron is there. They have different number of core electrons, different number of protons, different number of neutrons, all these different things, but they undergo similar reactions because they have the same valence electrons. So chemical reactions actually follows completely two valence electrons. Nuclear reactions we'll learn about later doesn't use valence electrons, but 99% of reactions are all based on the valence electrons. So just as a refresher, the valence electrons are the outermost electrons in the Bohr model. So here, for example, we have 4 valence electrons in a carbon atom. Over here, this must be magnesium, number 12, we have 2 valence electrons. And you should be able to figure out how many valence electrons we have for different atoms that way. So one way that you can do that is draw out the Bohr model and look at it. Another way that you can do it is from the periodic table. I didn't show this to you before because I wanted you to think of them in terms of Bohr model and quantum rotation, but there's a shortcut to figuring out the number of valence electrons something has. Everything in the first column is going to have 1 valence electron associated with it. Everything in the second column has 2 valence electrons. Over here in the boron family, we have 3, 4, 5, 6, 7, and 8 for the noble gases there. So you just look at what column something's in, and you very quickly can see how many valence electrons it has. So if I just point, iodine has 7 valence electrons because it's in the 7th column. Over here, silicon's in the 4th column, so it has 4 valence electrons. And if we draw that out, that's exactly right. So silicon, if I draw out the silicon Bohr model, I'm going to have 2 electrons in the first one, and then 8 in the second, and then in the third, I'm going to have 4. So 2 and 8 is 10, 4 is 14. We look, silicon is atomic number 14. So therefore, it would have 14 electrons, 14 electrons in its valence form without a charge. The quantum model, if we were to draw that out, 1s2, 2s2, 2p6, 3s2, 3p2. So here, again, we have 4 valence electrons as we look at it. And the same is true about carbon, it's just got one ring less. It has 4 there, 2 and 4 as you go through it. You guys okay with that? Will you accept that as I say that? Okay. And by all means, you can draw out the Bohr models and prove it for every one if you want, but I probably wouldn't. It's a lot of work. Okay. So, these valence electrons then are key to understanding reactions and understanding why atoms do what they do. So to show this, chemists use what's called an electron dot diagram. An electron dot diagram is really a shorthand to show the valence electrons in a given element. So up on the board we have carbon. You have 4 valence electrons. So the dot diagram is made up of 2 parts. The first part is the symbol for the element. So that's going to be the letter C. And then the number of dots you have corresponds to how many valence electrons you have. So in this case, we have 4 valence electrons. So we've got 4 dots around our C. This is another circumstance where high school teachers like to care a lot about where you put your dots and so forth. I don't care at all. Okay? As long as you've got 4 dots, I'm going to be happy with it. Now, to make your life easier, it's best if you put 1 dot on each side before you start to double them up. But that's just to make your life easier. I'm not going to count it wrong if you do it differently than that. So there's carbon, the symbol for the element, and then the number of dots corresponding to the number of valence electrons. In this case, it's going to have 1 on all 4 sides for 4. Silicon, for example, the dot diagram for silicon is going to be an Si, and then 4 dots around it as well, because there we have 4 valence electrons. Why don't you guys try on your paper, draw out what the dot diagram would look like for potassium. Potassium is K, number 19 on the periodic table. Okay, so potassium is going to be the symbol for the element, which is the K, and then 1 dot because there's 1 valence electron. And it doesn't matter what side the dot's on or anything like that, just 1 dot there associated with it. Does that make sense for everyone? All right. Just for formality, let's do one more. Let's do chlorine, number 17 on the periodic table. Okay. So chlorine then is going to be a Cl. And how many dots am I going to put around my chlorine? 7. 7. It's in the 7th column, not counting the transition metal. So 1, 2, boron's 3, carbon's 4, nitrogen's 5, oxygen 6, fluorine there is 7. So 7. So we'll put 7 dots around it. And that's a dot diagram. There isn't anything more than that to it. And it's really nice because we don't have to draw out all the E's for the Bohr model time and time again. It makes my life much, much easier.
Could that be like part of like a question where you would put, there would be a question and you would do the Bohr, and then obviously then would you say like part B of that?
Oh yeah, absolutely.
Put the dot diagram of what this cases.
Yeah. There's a question I ask after this chapter that does exactly that. It starts at the Bohr model, and then you find the number of valence electrons, then you use the number of valence electrons to predict the type of reaction that occurs, and then it continues on. So yeah, absolutely. So this brings us back to the octet rule. I think I mentioned this a little bit in the last chapter, but what the octet rule says is that elements are going to react so that they have filled valence shells. And these filled valence shells would have 8 valence electrons for the most part. The first hydrogen and helium only have 2 in its filled shell, but we won't worry too much about that. So the octet rule really means the rule of 8. So atoms are going to react so that they're filled shells. In a dot diagram, that means it's either going to get to 8 dots around it or 0. 0 would be if it gives up all of its electrons. Then it would have a filled shell in the next level down. And we see this time and time again. This is actually how things react. So chlorine, for example, here. Chlorine has 7 valence electrons. So do you think it's easier for chlorine to gain 1 more valence electron or give up 7?
Gain 1.
Gain 1. And that's exactly what it does. It gains 1 more electron and picks up a -1 charge. When it's gained that electron, it now has 8 valence electrons, and those 8 valence electrons make it stable. It's a really, really simple rule. You just think, oh, 8, that's too simple. That's really how it works. There isn't a whole lot more to it in terms of that. Potassium, on the other hand, potassium here has 1 valence electron, so it can either give up 1 or bring in 7. In that case, it's going to give up 1. So it gives up 1 to the surroundings, removing its 1 valence electron and picking up a +1 charge. And that's how it works. That's the octet rule, actually. So why don't you guys try phosphorus? Draw the dot diagram for phosphorus and then use the dot diagram to predict what charge it's going to have when it forms a compound. No. Oh, phosphorus, I'm sorry, 15.
Okay.
That's not a dumb question at all. I just kind of assumed when it's a periodic
you're
table
fine.
memorized.
I used to know the periodic table, but that was like in high school.
Yeah, it's not worth memorizing. Even when you're a professor, it's not worth memorizing. Okay, so to make sure we're all getting started on the right track, phosphorus is P. And how many dots am I going to put around my phosphorus? 5. So 1, 2, 3, 4, 5. Okay, so that is the dot diagram. Let's take another 20, 30 seconds if you need it to predict what charge it's going to take on.
So I have a question.
Of course.
If it takes on, it's negative, and if it gives away, it's positive.
Yes, because it's bringing in more negatives when it takes on. Okay, anyone want to share what they have? Yeah.
That P
go, -3, and that's exactly right because you're going to get 1, 2, 3 more valence electrons to fulfill the octet role. And that's exactly what phosphorus does in real life. You find phosphorus in a compound, it's going to be a -3 charge. Okay. Yes.
It's just, I guess, a technicality question.
Yeah.
Besides actually counting over periods, right, the columns of periods?
Yeah. No, the periods are down. They're groups.
Oh, the groups, okay. So besides counting over groups like 1, 2,
Mhm.
3, 4, 5, I know phosphorus has 5 valence.
Yep.
Aren't there other ways to determine the valence?
You can draw the Bohr model for it. And if you draw the Bohr model for phosphorus, you're going to see that there are 5 electrons in that outer orbit. And that will give you the number of valence. Or you could do the quantum model and look at it that way, either one of those. But that's really about it, I think.
I guess then I should have asked maybe. So with potassium,
Okay?
I did it that way. I thought in my head, okay, so there's 2 in the first orbit, there's 8 maximum in the second.
Mm-hmm.
So that's 10, and then there's 9 left over.
Yep.
But for potassium, didn't you just put 1 there?
Yeah, so potassium, because we've moved down to that 4th column, you really have to use the quantum model for that. 1s2, 2s2, 2p6, 3s2, 3p6, and then the next one after that is 4s1. Okay. So the highest number is 4. So you have 1 valence electron there. What you're having an issue with is 2, 8, and then 18. And in that case, if you're trying to do the potassium model in the Bohr, it would be 2, 8, and then 8, 9.
Yeah,
9 around the outside. The Bohr model actually breaks down once you move into that 4th column. So for those cases, the Bohr doesn't work. I guess that's what I'm trying to say there.
I guess that's where I was confused
And it is confusing. It absolutely is confusing. From a professor point of view, I won't ask you to use the Bohr model for anything past number 20, or past basically 17 there, because it doesn't work, or 18 there. But that being said, this is the actual explanation for why you end up with 1. But you bring up a good point that the Bohr model fails at that. Other questions? Yeah.
If there happens to be 4 valence electrons,
Okay.
does it typically give up 4, or does it take on 4 more?
Okay, so carbon is the perfect example of this. Carbon has 4 valence electrons, so the question is, does it give up 4 or take on 4? It really does both. It depends on what it's matched with. If it's matched with something that wants to give up electrons, then it takes them. If it's matched with something that wants to take them, then it will give up. So for that reason, I'm always super careful about the 4th column, not putting it in questions because you don't really know. So anytime we're doing something like this, well, I shouldn't say anytime. My intent is never to give you the 4th column because of the fact right there. You don't know whether it's giving or taking in that regards. And that's true, actually. In carbon, it exhibits both a +4 and a -4 charge when you look at it in real life. It can do either or.
At what point would we get to the explanation as to how to figure that out?
Well, it really is just what I said. It's what it's paired with. But you won't in this course. I mean, I guess I just did, but yeah, I won't ask you to call that. There are compounds that have carbon that we will do when we get a little bit later on, but for now, we won't worry about it.
So if we look
Yeah.
at, SE 34.
Okay?
It being in the
Yep,
It would have 6 valence electrons?
yep.
Okay.
Exactly right. Yep. That's what's really nice about counting the columns like that, because you can just say, oh, second column, 2 valence electrons, and so forth and so on.
So why is the middle skipped?
All right, so the middle is skipped for a couple different reasons. One is because they're filling out of order, it complicates things to a certain extent. The other thing is transition metals can have more than one charge. So like for example, selenium, Se you just said, has 6. So it's always going to take on 2 to get to 8. And that's what it does. Okay, so it's very easy to understand that. Transition metals though really depends on what they're paired with for what the charge is. And even then they're not always the same. So iron and chlorine can react as FeCl2, FeCl4, FeCl6, FeCl8. So any of those different ones. So the iron in all of those are taking on different charges. It's a 2 plus 4 plus 6 plus and 8 plus as it goes through. So just looking at the periodic table, you wouldn't be able to figure that out. I can't figure that out just looking at the periodic table. And it has to do with the fact that those Ds sit in a weird position in terms of what they are. They're not truly valence electrons because they're not S or P, but yet they can play some part in it.
Okay.
So I won't ever ask about the transition metals in regards to these types of things. So they're out for now. Answer your question, okay. Anything else? Okay. So this is called the octet rule, and it's really just the rule of 8, saying that things want to act as noble gases. They want to get to 8 valence electrons, or 0, which basically gives them a filled shell on the level below as they go through it. So we can start to see how this explains certain things. Sodium has the Bohr model drawn here, which would be our dot diagram with 1 dot. That's going to give up the dot to form the +1 charge. Chlorine is the opposite of that. Chlorine, on the other hand, has 7 valence electrons. It's going to bring in 1 more to form this negative charge with it.
Oh,
Yeah.
I think I understand now. Let me just make sure this is
Okay.
right. So, you know how like when we're doing like I forgot, but it's when we do the 1s
Mhm.
to, what is that called again?
Quantum
The
notation.
Quantum. When we do the quantum, like, if like the last thing it's supposed to be 6 and we break it down to like 5 instead of it being like P6. Bring it up.
Okay.
We're trying to get to 6 and we do plus, you see, am I?
Yeah, so if we have 5, we want to get 6. We're going to add 1 more.
Right, so that's, we're trying to even it out by adding a charge.
Yep, that's exactly
Oh,
what
okay,
we're
that
doing.
makes sense. I didn't know why we were actually
Yep.
doing it.
So I wouldn't worry too much about the quantum model there. Just worry with the dot diagrams getting to 8.
Okay.
Because that's what it is. Now, in your case with the P6, you've actually got the S with it too. So that's 2 and then the 6 to get to 8.
Okay.
Yeah.
So for each, is the ring, it's called electrons?
The electrons are in the rings. They're
Okay.
called orbits.
So for each ring, after the first one, which is, you can only put 2 in there, it's just 8 for each one.
Yeah.
So every time it just adds 8.
Yep.
Okay.
We're just, as far as the rule, the octet rule is concerned,
Alright.
yep. 8's your magic number there.
Okay.
I asked the class yesterday if Schoolhouse Rock was still a thing. They said it was, so hopefully you've heard of Schoolhouse Rock and the magic number. I don't remember. Never mind. You guys don't care. I'm gonna get started. Okay, so chlorine is going to gain 1 electron then, so that it fulfills the octet rule as well. Now, obviously, sodium can't just give up an electron and have it go off in nowhere, and chlorine can't just magically create an electron from somewhere. So these things pair up. And this is how we show a reaction that occurs like that. Sodium chloride is table salt. It's normal salt that we have. Most people just call it salt. So sodium here has 1 valence electron that it wants to get rid of. Chlorine has 7 and it wants to take 1. So sodium says, great. I'm going to give up my electron over here to fulfill the octet of chlorine. That's going to make the sodium happy because it has 0 valence electrons. It's going to make the chlorine happy because it now has 8. So sodium has given up all of its electrons. Chlorine has gotten 8 in its shell. Both of them are happy, so they form a compound here that looks like this. So sodium plus chlorine reacts to form sodium chloride. And this is the way reactions occur. This is one of the 2 major types of reactions. These are actually called an ionic reaction. Ionic reaction. And the reason they're called an ionic reaction is because they have ions. Sodium has given up its electron, so it gains a charge, and that makes it an ion. Chlorine has gained an electron, giving it a charge, and that makes it an ion as well. So, and the reason why these ions stick together is because of the charges that are created. So sodium has a positive charge, chlorine has a negative charge, so you've got 2 charges of opposite signs. The opposites attract, so they stick together then. And that's an ion, an ionic bond, or an ionic reaction there. So ionic compounds are actually held together by this attraction between the positive charge and the negative charge, just like 2 magnets are. If you've ever heard the saying opposites attract, that's where this actually comes from for real. Magnets and then the charge is attracting. 2 charges of opposite sign are going to be drawn to one another. And there they stick together. And you can explain this using our dot diagrams. Does that kind of make sense? I mean, we're going to talk a lot about this as we go through, but okay. So, as I said, this is one type of bonding that occurs. There are actually 3 major types of bonding. We're only going to talk about the first 2. I just want to mention the third one so that you're familiar with it. The first type of bonding is ionic bonding. Should be N. Attraction of charges between ions. So when you've got a positive charge and a negative charge, this is when you see ionic bonding. This occurs because you're transferring electrons. Your sodium is giving up an electron, your chlorine is taking an electron. That's a transfer of electrons. Generally, this occurs between metals and nonmetals. As far as this class is concerned, ionic bonding is between a metal and a nonmetal. That's always going to be the case. And the reason for that is because metals want to give up their electrons, and nonmetals want to take the electrons. If we look at the periodic table, metals are on this side of the periodic table, which are the ones that have low valence numbers, so they can give them up easily. Nonmetals have the high valence numbers, so they want to take the electrons. So that's ionic bonding. The other type that we're going to look at extensively is called covalent bonding. And in covalent bonding, we don't have a transfer of electrons, we have sharing of electrons. So an electron is going to spend a little bit of time on atom 1, a little bit of time on atom 2. And this is going to fulfill the octet rule because that electron is going to be counted for both atoms there. Covalent bonding occurs between nonmetals. And the reason why covalent bonding occurs between nonmetals is because neither of them want to give up an electron. If you've got 2 nonmetals, they both want to bring the electron in. Neither of them want to give up electrons. So they end up sharing it between the 2 atoms involved. And then finally, metallic bonding. Metallic bonding is bonding between 2 metals. And there the electron is just free to go wherever it wants, basically. We won't really talk about it any more than simply saying its name right here. It does occur. It gives metals their properties and so forth, but that being said, it's not something we're going to cover in this class. We're going to just concentrate on ionic and covalent. And one of the quickest things for you guys to learn about that is ionic is between a metal and a nonmetal. Covalent is between two nonmetals. So if I have a reaction that's occurring between calcium number 20 and fluorine number 9, is that going to be ionic or covalent? Ionic. Ionic. Calcium is a metal, fluorine is a nonmetal, so that's going to be ionic. If I have a reaction between oxygen number 8 and chlorine number 17, is that going to be ionic or covalent?
Covalent.
Covalent, because they're both nonmetals. It's as simple as that. And you're going to have different rules for the different types. So the first thing you're going to have to do is identify which ones are covalent, which ones are ionic. Now, sodium chloride. Sodium and chlorine. Would you expect that with what I just said from the periodic table, would you expect that to be a ionic or a covalent?
Covalent.
Sodium is number 11 on the periodic table. Chlorine is number 17.
Ionic.
Ionic. Sodium is a metal. Chlorine is a nonmetal. So those together are going to be an ionic compound. And it does, because the electrons transferred over, it creates ions, and then we've got an ionic bond occurring there. And we're going to work with these. It's not like that's all you get, and you just got to learn or something. This whole chapter is about bonding and the different types and so forth. So, ionic bonding. Ionic bonding is formed from ions. There are two types of ions. A positive ion is called a cation. A negative ion is called an anion. You notice my little picture up there of the cat? It's got pluses for the eyes. And that's how I remember a cation is positive. First time I saw that picture, I was in a class just like this, a first year or first level chemistry class. And my professor was super, super prim and proper. If you did call him doctor when you asked him questions, he basically kicked you out of class. He wore like a tweed jacket, had a pipe. He used to smoke in the lab and blow the smoke into what we call fume hoods so no one would know. Super, super uptight and everything. But then one day, out of nowhere, he drew that up on the board. This incredibly prim and proper professor. He drew this picture of a cat. And because of that, ever since to this day, I remember that. That one I stole from online. The one that he drew had 6 whiskers. That's how much I remember it, just because it was so out of place for him to actually draw a picture on the board. But cation are positives because the cat has pluses for the eyes. I kind of like this one. I have never heard this one. An ion that's positive. I thought that was kind of clever too. I'd never seen that one before, so I threw that one up there. I like cats. I don't know. It just sticks with me. If it can help you remember, then more power to it. I'll gladly embarrass myself up here if it helps you remember cations and anions. Cations are positives, the anions are the opposite. They're negatives. Now, these positive and negatives don't want to be next to each other. So if you've got 2 positives, they're going to push apart from one another. 2 negatives will do the same thing. So because of this, when you've got positive and negatives, they like to alternate. They like to have a positive, then a negative next to it, then a positive, then a negative. And you see this especially in 1-to-1 ratio compounds like sodium chloride, where you have 1 positive ion sodium, 1 negative is chlorine. So this is the structure of sodium chloride. The greenish spheres here are your sodium. The purple ones are your chlorine. And if you were to look from the top, you'll actually they've got this reversed. Wonder why. they've got them alternating as they go through it. So you've got a positive here, then a negative, then a positive, a negative, positive, negative, positive as you go through it. So in ionic compounds, you don't have just two atoms stuck together. You have millions and millions and millions of atoms stuck together. And they stack in certain orders. So sodium chloride actually stacks as little cubes. If you look at salt, and I would bet money none of you have ever looked at salt at this level, but if you look at a little tiny grain of salt, okay, basically the smallest ones you can see and so forth, they're going to be little cubes. Salt is actually cubes when you sprinkle it out. And the reason why it's cubed is because of this alternating arrangement here. A cube is the most efficient way that it can go and keep the positives away from the negatives and so forth. So next time you use salt, just don't make it obvious, but take a look at it and you'll see they're little tiny cubes. Sometimes they're diamonds, which are just cubes on their corners, looking down the side as it goes through it. So that is if you have a 1-to-1 ratio, but if you have other ratios, it gets much more complex. Calcium, for example, here, calcium is a 2+, fluorine is a 1-. So you have 2 fluorines for every 1 calcium. So you can't just alternate. You can't have positive, negative, because you have twice as many fluorines. So you get to much more complex arrangements here. And this is why we've got crystals of different shapes. So when you look at ionic crystals, you'll see cubes, weird looking diamonds. Sometimes you see needles. I don't know. Different shapes as you go through it. You guys probably know possibly better than I do. But then you end up with different shapes because of this desire to keep the positives and negatives away from one another. You guys have all seen, oh, here's a good example. Gemstones. Okay, so like emeralds, so forth. If I have an emerald, I can't just cut an emerald in whatever shape I want, right? There are certain shapes that it can take. Diamonds are the same way. You can only cut them in certain arrangements. Like, they have names. Princess cut, I think that's one. Is the emerald cut one? Maybe, cushion, I don't know. They're different things. I bought a wedding ring 20-some years ago. That was the only time I ever looked into these. Anyway, there are certain cuts you can have. And the reason is because when you're cutting a crystal apart, you can't cut through the middle of an atom in some weird direction. You've got to cut along these lines. And that's what the facets are for the various gemstones. So different gemstones will actually have different ways they can be cut. There are some that overlap, obviously, but sometimes you just can't cut a certain gem in a certain way. So you see that. And you also see it when you look at minerals and stuff, they have different shapes and so forth because of this. And it all goes back to these charges and keeping the charges away from one another. The other thing I just want to stress here is even that smallest little bit of salt that you see when you're looking at it, that's not like 10 atoms by 10 atoms by 10 atoms. That's billions and billions and billions of atoms there. Remember how small atoms were when we zoomed in? To be able to get something that you can actually see, it takes tens of billions of atoms before it actually starts to build up to that.
I just have a question.
Yeah, of course.
Slightly off topic.
It's okay.
Maybe you can answer. Why is it true that diamond can only cut diamond, and if so, why?
No, it is not true. Diamond is the hardest natural material known to man. So for that reason, you would expect that other things could not cut it. So they used to say if you want to prove something's really a diamond, take it, see if you can cut through glass with it, and so forth. That's not exactly true anymore because there's other materials that are strong. But it's the strongest natural material that we know of. So you wouldn't think that you could cut it with other things. That being said, you can't. It just damages whatever you're cutting it with. So like if you're cutting it with a chisel, which is basically how they do it, they line it up and so forth, it's going to damage the chisel, but who cares? You know, and so forth. You just get another one. And things line those lines. And that's how they cut diamonds. When you find a diamond, it's not in the shape that you see in a ring or in a gem store or something like that. They're very, very messed up shapes. Okay? And then a jeweler goes in and cuts them to a variety of different smaller crystals as they go through it. So you absolutely can cut diamonds, and people do it all the time. When they find them in nature, they're called uncut, actually. That's what they call them. And then they cut them into smaller pieces that look pretty, and that's the cut diamonds.
But they have to follow those lines.
And they have to follow those lines, and those lines define the shapes that you can get. That's why in diamonds there's only certain shapes you can get. I don't know what they are. I should probably look it up sometime. But that's the idea. And the same thing goes for other gems too. Like, the Hope diamond, for example, was this big, huge thing, right? But it's not cut down to the smaller shapes. A while ago, they tried to sell like the biggest diamond found in nature, and it's not very pretty, but you could cut it into a whole bunch of littler diamonds and sell them off and so forth. So it's not something you want to do on your own, though. Just so everyone's aware, don't go home and try and cut a diamond into 2 diamonds. It won't end well. It takes a lot of practice and so forth, apparently. I've never done it, so I don't know, but I'm told it takes a lot of practice to do it. Okay, let's see what's, I assume that answers your question okay.
It does.
Okay.
Thank you.
Okay, so I think that's where we're going to end off for material today. We're going to start using these to predict the formulas and so forth, but that's going to take a lot more than 5 minutes. So we're going to end with that for now, and then